So this is the second part of section 8.2, where we will be conducting a hypothesis test using what we call the p-value method. For the traditional method, we used the critical value, and then we used area to help us find, or that alpha value to help us find the test score, and then or the test value, and we compare the test value to the critical value as a way to separate the non-critical region from the critical region. The p-value is going to differ slightly, so there's going to be two steps that change a little bit. But all the alpha levels we've been looking at have pretty much been the same. Again, the common alpha levels are the 5%, 1%, and the 10%. And this all depends on the seriousness of that type 1 error. Remember, alpha is the probability of creating or allowing that type 1 error to occur. Besides listing any alpha value, many computer stat packages give a p-value for a hypothesis test. So that's something that we're going to conduct by making a sketch to help us connect all the pieces, but we'll be doing this with our calculator or something online if you guys don't have your own calculator. All right, so the P in p-value stands for probability. It's the probability value. It's the actual area under the standard normal distribution curve, and it's representing the probability of a particular sample statistic or a more extreme sample statistic occurring if the null hypothesis is true. So just as a quick example, just to relate what the p-value is. Let's say our null hypothesis was some population mean is equal to 50. Our alternative hypothesis is that mu is greater than 50. Let's say we have a sample mean of 52. Let's say we type this into our calculator or computer software, and it gave us a result of a p-value being this 0.0356. That just means it's the probability of getting a sample mean of 52 or greater if the true population mean is 50. So this is just a normal distribution. Notice my mu isn't 0 here, but right in the middle, we're looking at our population mean as being 50, and then our sample mean is 52. So this area to the right of the 52, that is the p-value. That's what we're going to be finding. In the end, we're going to compare this to our alpha. And on the next couple pages, I'm going to take you through the different scenarios with a right tail test, a left tail test, and then a two tail test as well. But just kind of showing you if we get an alpha value that happens to be over here, there's going to be a way that we compare it. So if everything that would be shaded, I'm not going to color in over this though, but if this were alpha, let's say this is at a 10%, we would make a decision based on this. So in this case, we are going to be comparing p-value to alpha to help us make our decision. So we're looking at areas here, so shaded regions versus the critical numbers. So I don't really have a critical value separating my critical region from the non-critical region. So let's take a look at the steps and how they're a little different from what we already looked at in the first part. So the p-value method, again, there is no right way to do this, saying the p-value method, like you have to figure out if you have to use a p-value method or not. It's your choice ultimately as a researcher. For just getting started with these, I'm going to tell you if I want you to use a traditional method versus the p-value method, or sometimes I say it's your choice. Step 1 stays the same though. We're still going to state the null hypothesis and the alternative hypothesis, then identify the claim. However, now step 2, notice there is no step saying that we calculate the critical value. The test value jumps up now to step 2, where it was step 3 in the other test. We compute the test value. It's still the same formula, that z is equal to the difference of our sample mean. So that always goes first, minus our population mean over that standard error. Step 3 now, we're going to use this test value to find the p-value. So this is where we type in our test value. It's either the lower boundary or it's the upper boundary, depending on what type of tail test we're using. Then we compare that p-value to our alpha to help us make our decision to either reject the null hypothesis or we do not reject the null hypothesis. And then we summarize the results just as we were doing in the traditional method. All right, so our decision rule when using a p-value. So if our p-value is less than or equal to alpha, then we end up rejecting the null hypothesis. if our p-value is greater than alpha, we do not reject the null hypothesis. All right, so let's take a look, an example here when we have a left-tailed test. All right, so I'm just going to say, let's say we have a test value of a negative 1.94. I'm going to put that over here. Now this will give us a certain area to the left of it. So we're going to use this negative 1.94 to find the p-value. Now this is, if you're using the calculator, you go to menu 552, and we're going to type in this negative 1.94 as our upper bound. If we do that, then we get an area of 0.0262. So let's say alpha was already decided to be 0.05. So we would compare our p-value to alpha. So our p-value is 0.0262 and alpha is 0.05. So our p-value is less than alpha. So this is what it would show up like on our curve that's over here. So if we're looking at this purple area right here, so if I were to shade over this way, this is alpha is equal to 0.05. What I have here in red is our p-value at 0.0262. So it's like this purple area, because it would consume this, that this is locked in. And since alpha is the probability of committing that type 1 error, then we don't want that to happen. So in this case, we end up rejecting. So our p-value is less than, in this case, less than alpha. So we end up rejecting the null hypothesis, meaning that was in the rejection region or the critical region. Our entire red area that we shaded here is in that purple area, and that whole purple area is the rejection region. I'm going to change the alpha level just to show you a different scenario. So I'll make another sketch here. So think of, again, the area for alpha, any area that falls within that, that's completely consumed in that alpha area, that region, we end up rejecting the null hypothesis. Think of that as the critical region. So again, if I'm looking at this negative 1.94, that this is now my p-value still right here. This is the 0.0262. But now let's say alpha is equal to 1%. So if I compare my p-value to alpha, this is the 0.0262 compared to 0.01. This is now greater. Graphing this over here, let's say that this part right here is alpha is equal to 0.01. Everything in purple there I would reject, but since I have a little bit of red that's not in that purple region, it's beyond it, now it's into the non-critical region. So this is why we would say when our p-value is greater than alpha, we do not reject the null hypothesis. So this is how it's going to be different. We could look at it visually over here, or just straightforward follow the rules of comparing them with the decision rule that I have at the top. We're going to go through a couple actual examples here, but I just want to show you what we're looking at, what the images, the visuals look like for a left-tailed test and a right-tailed test. All right, so looking at a right-tailed test, because we're going to be on opposite sides. That's why I don't want to say if it's to the right or to the left, because it's going to switch here. So now let's take a look at if we had a positive 1.94 for our test value. And let's say alpha again was, we'll go to the 0.05. So let's say, I'm just going to shade this all in green. All right, so our p-value is still going to be 0.0262. And you could try this if you go to your calculator, type in a positive 1.94 is a lower boundary. You should still get this 0.0262 as our area. But now if alpha is a 0.5, that means our p-value is going to be less than our alpha. So just showing this over here, if this were the alpha equals 0.05, again, here's this purple region that's going to consume the green, the p-value that's right there. So this is why I don't want to say when it's to the left or to the right, that we just want to say it's greater than alpha or less than alpha. So in this case, because everything in purple here is where we would reject, we still keep that decision. So we end up rejecting the null hypothesis. If our alpha is a 0.01, again, that might show up here. So that red. Keeping in mind, alpha is chosen before, so we can't change it afterwards. I'm just showing you two different cases here for each one. Then our p-value is greater than alpha, so we have that chance of that green region showing up outside. So this is where we do not reject the null hypothesis. Now here, because it was just a one-tailed test, our p-value stayed the same, but as you guys have seen in the past, when we have a two-tailed test and we have to split alpha to alpha over 2, something else is going to change with our p-value as well. So let's take a look at a two-tailed test. Here it says we're going to use the test value. It's up to you. The test value is still going to stay the same. That doesn't get split or cut in half. We're going to end up having a positive or negative. So we only need one of them to find the area below it or the area above. So we use a test value as a lower boundary if it's positive, and the upper boundary if it's negative. Then we're going to double the area obtained. So if I'm drawing this out, and let's say I have this negative 1.94, and then I have a positive 1.94. So the area I get here is going to be this 0.0262, and then the area I get here is also going to be a 0.0262. So that means my p-value is the combination of them, because I need to compare it to alpha. So that's going to be 2 times the 0.0262. Because if I compare to alpha, let's say, use a different color there. Let's say alpha is the 0.05, then I'm going to have alpha over 2 show up here, and then alpha over 2 show up here. So in order to compare the two separate red regions to alpha, I need to double it. So the p-value gets doubled here. So that's what this is saying. So let's actually take a look at some examples. I have 2 examples here. Okay, here a researcher wishes to test the claim that the average cost of tuition and fees at a 4-year public college is greater than $5,700. She selects a random sample of 36 4-year colleges, finds the mean to be $5,950. The population standard deviation is $659. Is there evidence to support the claim? So remember, when we say support the claim, that means our claim should be the alternative hypothesis. At an alpha level here of 5%, we're going to use the p-value method. So if we go back up to the top, a researcher wishes to test the claim that the average cost of tuition and fees at this college is greater than $5,700. So step 1 is we're going to state the null hypothesis would then be that mu is equal to 5,700. Alternative hypothesis is that mu is greater than 5,700, and then this is also our claim. Now step 2 is to find that test value. So we're going to say the test value, again, which is really z, is going to be this 5950. Remember, it's X bar. Let me plug my computer back in. Okay, minus the 5700 divided by the 695 over the square root of 36. I want to pause that to calculate it real quick. We should be getting 2.28. All right, now we have to find the p-value. All right, so since this is greater than, we're looking at a right-tailed test. So we're going to say this is where our 2.28 is. What I have shaded here in blue is the area we're looking at. So this 2.28 is going to be the lower bound. So if you hit menu 552, type in the 2.28 as the lower bound, and then the infinity as the upper bound, or that 9e to the 999 that you need to have on there. Here, the p-value should turn out to be a 0.0113. So that's what this part is right here, the probability of getting this area. All right, now we need to compare the probability or the p-value to alpha. So I'm just going to write it here. P-value compared to alpha. So we have a 0.0113 compared to a 0.05. So 0.0113 is definitely less than 0.05. So that tells me my 0.05, my alpha, is going to be a larger area. So let's say we take it out to here. I'm just drawing it larger so we can get a better view of this. That means this green area is going to consume that blue area, because this is alpha equal to 0.05. So that means the probability of committing that type 1 error is going to show up here. So we end up rejecting the null hypothesis. And our summary then is there is enough evidence. We can just go right to how it's worded in our question here. There is enough evidence to support the claim. And for just these examples, I'm going to just write it out and stop right there. There's enough evidence to support the claim. So it's like we kicked away the null hypothesis and we're going with our claim here. But again, we can't say that we can prove it. It's just there's enough evidence to support the claim. Again, that claim was that the average cost of tuition and fees at a four-year public college is greater than $5,700. All right, we just have one more example. Again, it's saying a researcher claims that the average wind speed in a certain city is 8 miles per hour. A sample of 32 days has an average wind speed of 8.2 miles per hour. Standard deviation of the population is 0.6 miles per hour. Again, at the alpha equals 5%. Is there enough evidence to reject the claim? So notice if it's saying reject the claim, because it's using the word reject, that means our claim should be the null hypothesis. And if we go back up here, they're saying that it is 8 miles per hour, and then our sample mean was the 8.2. So in our first step, our null hypothesis is that mu is equal to 8 miles per hour. Then the alternative hypothesis is that mu is not going to equal 8 miles per hour. We have no other statement here giving us direction of less than or greater than. But if the researcher is claiming that it is equal to, we finally have an example where the null hypothesis is our claim. Or vice versa, our claim is our null hypothesis. Step 2, we're going to find our test value. So again, this is z is equal to 8.2 minus 8 divided by this 0.6, that's divided by radical 32. Go ahead and pause this and calculate this. And we should be getting a 1.89. So if we make our sketch, if it's not equal to, this is a two-tailed test. So that means I'm going to have a 1.89 on this end, and then a negative 1.89 on this end. Even though it came out to be a positive for our test value, we're still going to put in the plus or minus. So this is telling me this area that's over here, whatever I find, I need to double it because these areas are going to be the same. We're just using one of these ends to help us find the area here, but we need to double it to get our total p-value. The p-value, just like alpha, is going to be the two split tails added back together. So I'm going to use the negative 1.89. Remember, that's going to be our upper boundary. So when you go to calculate the p-value, menu 552, keep that negative infinity there, and then type in a negative 1.89 as your upper boundary. So the p-value is going to equal 2 times the area that we're going to get. And you should be getting a 0.0294. And then this should give us a 0.0, we'll say 59. So our p-value is 0.059. Our alpha, so we're going to compare our p-value to alpha, 0.059 compared to 0.05. And now this p-value is greater than, so we do not reject the null hypothesis. So what we could say here is that there is not enough evidence to reject the claim that the average wind speed is 8 miles per hour. So again, we can say there's not enough evidence to reject the claim. So again, what's happening here is the alpha over 2 then is going to equal 0.025. So in this one, just this little part right here, this would be the 0.0294. So technically, yes, you can compare the 0.0294 to alpha over 2, but it's going based off of what the steps say. In particular, this is what we're looking at. We always want to compare it back to alpha, so we double the little bit of area that we get here. But what this is saying is that this 0.025 is only going to show up like right about here. We'll still have a little bit of this red, this 0.0294. So that's what we're looking at. So the p-value method is a probability value that we're comparing areas this time. So I do want to give you guys some time to work on this, so you'll have over the weekend. I'll post answers to the rest of worksheet 8.2 on Monday, and still give you Tuesday to work on it and ask questions. On Tuesday, I'll probably kind of take a break from chapter 8 and give you the final exam review for just chapter 1, and maybe a little quiz or graded problem over 8.1 and 8.2 I will post on Tuesday or Wednesday. So your assignment for today, after I talk about some things here, is just going to be to finish worksheet 8.2. So I've mentioned this before, but just to reemphasize that alpha, again, is chosen by the researcher before any statistical test is conducted. Remember, you're just testing your hypothesis. You're not trying to make your hypothesis right or make it wrong. It just is what it is once you go through all of these steps. The p-value is computed after the sample mean has been found. Sometimes it'll be given to us. Other times, if there's raw data, we have to find it. Now, even if what our statement says at the end leads us to support a claim or reject a claim, we still have to use common sense on what it's saying. So here's a good example. Statistical significance versus practical significance. If a researcher shows a new fuel additive increases the miles per gallon a car can get by 1/4 of a mile for a sample of 1,000 cars, is it going to be practical? So researchers must use common sense when interpreting results of their hypothesis test here. Is it worthwhile to market this product if it's only going to gain a little bit? So even though we're saying, yes, we could support this claim, is it going to be worthwhile in the long run? So these are just some things to look out for, to keep in mind. There might be some questions after a hypothesis test that I ask you to go through to maybe answer a question that might fit this little tip here. All right, so as I mentioned before, just over the weekend and on Monday, continue to work on worksheet 8.2. I will post answers to 8.2 for the rest of it on Monday. Take questions if you guys do have any. Please let me know. If not, keep up the good work and have a good weekend.